Oh, okay.
All right, welcome everybody. So let's get started. Before I introduce today's speaker, let me remind everybody that the recordings of all of the previous talks for the semester are available at the webpage of the New York Group Theory Seminar. So there are links to the YouTube videos of those talks. You're welcome to watch them there. And we'll try to post a recording of today's talk as well later on tonight. So as usual, once the speaker begins talking, please put yourself on mute. And if you have a question during your talk, unmute yourself and then ask a question. After the talk, as usual, so once the record button is off, so you're welcome to stay for an extended period of chat and informal discussion. You don't have to disappear right away. So we do that in lieu of wine and cheese. So, and with that said, I'm pleased to welcome today's speaker is Benjamin Steinberg from the City College of CUNY, and he's going to tell us something about simplicity of Nekrashevych algebras of constructing self-similar groups.
Okay, thank you, Ilya. It's good to be here in New York, and I'm actually in New York, so that's kind of, I guess, a novelty. First of all, I should mention this is joint work with Nora Sakats, who's currently at York, but also based in Szeged in Hungary. And so this is about simplicity of Nekrashevych algebras of contracting self-similar groups. So the group theory part of the seminar is the self-similar groups. The ring theory part of the seminar is the Nekrashevych algebras. And because it's me speaking, of course, semi-groups will find their way in at the end, depending on how quickly I go. If you're lucky, maybe they won't make too much of an appearance. Okay, let's hold on a second. My screen seems to have frozen. Oh, that's the outline. So the last section is the part where if I get to it, it will be a little bit technical. So hopefully I won't get too far into that. And if I do, it's because you guys didn't stop me enough. So let me start with rooted trees, because self-similar groups are groups that act on rooted trees. So X in this talk is always a finite alphabet, and it always has at least 2 elements, because this kind of theory is not interesting when there's only 1 element in your alphabet. And then the calligraph of the free monoid, X star, I'm going to denote the calligraph by TX because it's a regular rooted tree, so T is for tree. And this is how I draw it. In particular, I don't really want to think of this as I don't want to think of the edges as being labeled, because I'm going to allow tree automorphisms, and I don't really care about the direction of the edges. I will label the vertices because that's convenient. So here's the calligraph of the free monoid on 2 generators. And when you stare at it, one thing that's kind of important to notice, we'll see how my pen writing skills work on this. One thing that's important to notice is that we kind of have 2 trees, T0 and T1, hanging off the main tree that are isomorphic to the original tree. And it's the fact that you have these isomorphic subtrees that kind of makes the theory of self-similar groups work. And now let me just briefly say, what can an automorphism of this tree do? I'll have more on the next slide to be formal, but I think it's convenient while I have the picture to draw. So if I have an automorphism G, let's just imagine I have an automorphism here. What can it do? Well, it might swap these 2 trees. Since I'm doing a 2-letter alphabet, there's not too many choices. Or maybe it might not swap the 2 trees, but let's pretend that it does. Then this tree is going to move to this tree, and this tree is going to move to this tree. And since these 2 trees are isomorphic to the original tree, and in a kind of canonical way, because of the vertex labeling, the isomorphism is just erase the first letter. And so this map here that takes T0 to T1 is given by another automorphism, which I'm going to call G restricted to 0. Well, that's how I'm writing it. It's called the section of G at 0 because it's not really a restriction. And similarly, I'm going to write G sub 1 for the automorphism of the tree that takes T1 to T0 after we've identified the trees. So I'm going to write this formally on the next slide, but I want you to have this idea in your mind that an automorphism of the tree, what it does is it permutes the vertices that are at distance 1 from the root. And then the other trees these trees are all isomorphic to each other, and it moves them around according to other tree automorphisms. Okay, and let me point out that the reason why the root is fixed is notice that the root has degree 2, but all other vertices have degree 3. So the root is the only vertex of degree 2, so every automorphism of this tree has to fix the root. There's no place else for the root to go because the root is the only vertex of degree 2. Another thing I want to point out is the boundary of this tree. You can think of as the infinite paths starting at the root, and they correspond just to infinite words over the alphabet X, right? Like if I take the leftmost branch of this tree, if I just go along this branch, that's just 0, 0, 0, 0, 0. If you were to read the labels, which I didn't draw, they would label 0, 0, 0, 0, 0. So that's the idea. So that gives you a correspondence between infinite words and the boundary of the tree, and it's a homeomorphism in the usual topology. So in particular, the automorphism group of this tree and all its subgroups act on the infinite words, which will be important later in this talk. Okay, so let me move. So now I'm basically going to just write in a slide what I tried to draw for you guys in pictures before. So hopefully with the picture in mind, this will help. So every automorphism must fix the root because the root's the only vertex of degree the size of the alphabet. All the others have one bigger. Then it has to permute the subtrees with vertex set starting with X. So this is my T0 and T1 from before. So if I go back to my previous slide, my T0 and T1 were those two trees starting with 0 and 1. So TX is the tree of all words starting with X. And if my automorphism takes the tree corresponding to X to the tree corresponding to Y. So this was like my picture of swapping before. So here's TX, here's TY. If G takes this guy here, then it's going to take this thing here by another automorphism, which I write as G restricted to X, even though it's not really a restriction, that's just a convenient notation for it. Sorry, I do undo for my annotations. I'm sure there's a more intelligent way to do this. So algebraically, you can write it in terms of words without ever talking about trees by saying that G acting on a word XW is you apply G to the word X, to the letter X. That's just saying that the TX tree goes to the TY tree. And then you apply the restriction guy to the rest of the word. That's saying that the subtree under X goes to the subtree under Y according to the guy GX. And this G restricted to X guy is called the section of G at X. That's what the self-similar group people like to call it. And similarly, you can define sections at any word. So I have my tree and I have a vertex U. There's still a tree under here. This will go to some other guy, which is G of U. And then this guy will still move here by some other tree automorphism, which I'm going to call, sorry, that's G restricted to U, not G restricted to V. That's a typo, which I call G restricted to U. And so you can play the same game. So you can define sections at any word. But it turns out that if you know what sections at letters look like, you essentially know what sections at words look like, because the section at a long word is just the section of the section of the section of the section. So if you know how to take sections of all your guys, then you know how to take section at letters, then you can do it at words, provided you know how to take sections of the sections. Okay, so now I can tell you the definition of a self-similar group. It's probably pretty familiar to people in this audience, but maybe it's news to you. So a self-similar group is a group of automorphisms of this tree, which is close under taking sections. So what this means is that whenever I have an element of my group and it's acting on my tree, then this thing that's acting, taking this subtree to this subtree belongs to my group. So all the actions I see anywhere on the tree at any point belong to my group. If I just had a group acting on this tree, there's no reason the subsection belongs to my original group. And then I'm going to lose information because the self-similarity of the tree is not reflected in the group. These groups have the property that the self-similarity of the tree is determined by what happens, is reflected in the group. And in particular, it's enough to be close under sections at letters because then the sections at words are sections of sections of sections under letters. So as soon as you're close under sections under letters, you're also close under all sections. In particular, the whole automorphism group of the tree is self-similar for trivial reasons. And that's obviously not the example that we're very interested in because it's a big uncountable group. I mean, you could look at it in our setting, but it's not really what we're interested in. So now I'm going to kind of do some advertising for the theory of self-similar groups to convince you should care because famous groups belong to this family. So the probably the most famous self-similar group is the Grigor-2 group of intermediate growth. So it's a finitely generated torsion group of intermediate growth. There are also the group, the Sidke P groups for P and odd prime, which are also finitely generated infinite torsion groups. So these are all Burnside groups. Grigorchuk and Zook used a self-similar representation of the Z2 lamplighter group to disprove the strong form of a TS conjecture on L2 Betty numbers. And then that kind of inspired a group of work that eventually got a counterexample to weaker forms. I mean, there are a lot of forms of ATS conjectures. I'm not sure if there are some that are still open. Bartholdi and Nekrashevych used self-similar groups called iterated monodromy groups to solve Hubbard's twisted rabbit problem in complex dynamics. So self-similar groups aren't just like a fancy definition, they're like an important class of groups. And any self-similar subgroup of AuTX is going to act on infinite words because that's the boundary of the tree, and AuTX does. I guess I should mention here that, what was I going to say? Now I lost my train. I thought I was going to mention something about self-similar groups. And oh yeah, self-similar groups, the way I've defined them, were studied or introduced with this kind of definition by Nekrashevych in his book on self-similar groups, but there were kind of earlier forms of this that existed in the 70s in the Ukraine called automaton groups, and they're a special case of the more general definition, which doesn't even have to be finitely generated. So it's kind of an idea that evolved. The version I'm giving you is sort of Nekrashevich's final form of it, but it's an older idea. So now I'm going to tell you about automata because that's how you build nice examples of self-similar groups. However, I should mention that the definition I'm about to give of automata now is not very standard, but it will convert to the standard definition hopefully in a moment. That's my hope. So an automaton for this talk is a finite collection of automorphisms of this tree, which is closed under sections. So if you've never heard of an automaton before, that could be your definition. It doesn't have to be a subgroup. It's just a subset. In fact, it usually will not be a subgroup. However, if you've seen automata before, you probably think I'm crazy. So let me explain how this relates to standard automata, which are given by state diagrams. So the vertices or states of the automaton are elements of A. So I'm going to represent this automaton by a finite directed graph. So what I do is for each element, so for each, oops, I hit some button, that wasn't good. Okay, so for each vertex A, for each element of my automaton A, which is this finite set closed under sections, hold on, I lost my picture drawing ability. There it is. So for, I draw a vertex, which I label by the element A. I receive an input letter X, and then I output A of X. So these are input-output automata, or sometimes they're called transducers. And then my next state is the section. That's my next state. So if you're familiar with automata, that's how you think of it. The states are given by these letters. You get an input, you output whatever that automorphism does to that letter, and then your next state is the section. And that's how you're going to continue operating. And I'll have a picture on the next page showing you how to do this in a very concrete automaton. So let me just undo what I drew. So you'll see in a second how it works. But what's important is the subgroup generated by an automaton is always self-similar. This follows from basic automata theory stuff. And such groups generated by the states of an automaton are called automata groups or automaton groups. And they were studied since the 70s. I think Vlishkov already suggested studying them. And then Al Yashin, Sushansky, Grigorchuk, and others studied them. And one thing that's nice about automaton groups is they always have decidable word problem. Basic computer science tells you how to decide the word problem. I guess I was the first one to put it in writing. I can't believe I'm the first one to notice that the word problem, if you solve it the way automata theory tells you to do it, is in P space. And recently was proven by Jean-Philippe and others that there's an automaton with a P space complete word problem. So P space complete is the complexity for this class. So here's an example of an automaton, the adding machine. Okay, so if you look at this picture, if you're at A and your input's a 0, you go to B. That means the section of A at 0 is a B. And you output a 1. That means that A of 1 is 0. Okay, so that's a translation. Similarly, you can do the same with B. So B on any input stays at B, so the two sections are B, and on any input letter, it outputs whatever you inputted. So that's how it works. And then you can actually read what the transformation given by a state does to a word by just tracing the path and reading what you see on the right. So my input's a 1. So according to the blue label, just follow the blue labels, I output a 0. Then I'm still at the state A, so I get a 1, and I do the same thing again. But now I see a 0. So when I see a 0, I'm supposed to go to B and output a 1. B sees a 1 and outputs a 1, and that's what I do. So basically, by just tracing the path labeled by this word on the left and outputting the right-hand side, you can compute the output on any finite or infinite word. B does the identity because you always stay at B and you never change anything. And so the groups generated by these two states is just Z. A is of infinite order because it's actually adding 1 to a binary number with least significant digit first. That's why it's called the adding machine. Notice when I add a 1 to, if I add a 1 and my first bit is a 1, then I get a 0 and I have to carry, which means I add 1 again. Then I have to carry. Now I got a 1, I don't have to carry, so I'm done. So this is like adding 1, and so as you do this to bigger and bigger bit strings, you more and more approximate adding 1 to a two-adic number, or you can do it on infinite bit strings, and then you really are adding 1 to a two-adic number. So this element A has infinite order. Okay, so one thing that's quite important in the early work of Grigorchuk and Gupta-Sidki and others on their automata groups is that their groups were contracting. Okay, so this contraction property, let me give you how they originally defined it, then I'll give you the fancy modern Nekrashevych version. So roughly speaking, an automaton group is contracting if there's a constant lambda less than 1, so that the word length of any section is less than lambda times the word length of the word for all elements of sufficiently large word length. So this only kicks in when words are long enough. I should mention in any automaton group, it's always the case, sorry, I didn't mean lambda. I meant L, sorry. It's always true for an automaton group that the word length does not go up. Oops, I can't seem to write on my screen. So this is always true. That's true for any automaton group, but we want a strict decrease, and we want the strict decrease to be controlled by a factor lambda. Okay, so then when you have this, then if you keep taking sections along longer words, your word length will get smaller and smaller. If you take it along a word of length k, you're going to decrease by a factor of lambda to the k. So eventually you're going to get short words, and you can do induction, and that's used in the proof that the Grigorchuk group has intermediate growth and that it's a torsion group. Okay, and Nekrashevych actually defined this in a way that makes sense for any self-similar group, and the group doesn't even have to be finitely generated. We can't really talk about word length for a non-finitely generated group. So this was Nekrashevich's version. A self-similar group is contracting if there's a finite automaton. So that means a finite set which is closed under sections contained in G with the property that for any sufficiently long word, when you take the section of G, you end up in that automaton. And actually, this is then true also for all bigger K. So what this means is you take G restricted to W big is in K, is in N. So there's some finite set so that for no matter what word you start with, all sufficiently large sections belong to that element, that set N. And that set N is closed under sections. So once you're in N, you stay in N. What happens in N, which is called the nucleus, stays in the nucleus. And there's a smallest such N, a unique small such N, and Nekrashevych calls that the nucleus. There are algorithms which determine if an automaton is a nucleus. And if you have an automaton which is not a nucleus but generates a contracting group, then there's an algorithm implemented in GAP which will compute the nucleus. However, there's a caveat here. You need an oracle to tell you the group is contracting because it's not known whether you can decide if an automaton group is contracting. So what there is an algorithm which, if the group is contracting, will produce the nucleus, and otherwise it doesn't halt. So it's an enumeration algorithm. Nonetheless, it seems to work okay in a lot of, if you plug things into GAP. In the classical approach with this contraction by a factor of lambda, the nucleus is inside of those words, those elements of the group whose word length is so small that they don't contract by the factor lambda when you take sections. So contracting groups include many famous ones like the Grigorchuk group. Well, Grigorchuk has many groups, but most of the groups named after him are contracting. Gupta-Sidki groups, GGS groups, which stands for Grigorchuk Gupta-Sidki. There are Sunic groups associated to polynomials, which I'll define later. Automaton spinal groups, for those who know what those are. There's something called the Basilica group. There's the Hanaui Tower group on 3 pegs. So there are lots of examples. Of course, not all groups are contracting. Okay, so that's the end of my stuff on groups. And now we're going to go to rings. So maybe I should stop and check for questions first before I go into ring theory, because that's kind of a different subject. Any questions about some of these definitions? Because I know if you haven't seen them before, this could fly by pretty quick. Plus, if you don't stop me, I might get into semi-groups. That thread should work. Okay. This is the thing that I don't like about the modern world of Zoom. You have no idea whether anyone is following you, but okay. I guess in real life, you don't know either. Okay, so I guess I'll talk about algebras. So Nekrashevych, in a paper in Krell's, I forget the exact year now, or I'd say it was like mid-2000s, but maybe late 2000s. I forget the year now. He introduced C-star algebras associated to self-similar groups that generalize a famous C-star algebra called the Kunz algebra. But don't worry if you don't know what the Kunz algebra is, because you don't need to for this talk. But it's a famous one, so if I ever give this talk to an analysis seminar, it's good to have it there. Then Nekrashevych later considered ring theoretic analogs, where instead of doing C-star algebras, you take coefficients in a field. So Nekrashevich's C-star algebra is given by generators and relations. And if you have generators and relations, then you can define a ring. You don't have to do a C-star algebra. So the C-star algebra is a completion of the complex Nekrashevych algebra. If you take complex coefficients, then there's a natural way to define, it's a star algebra, and there's a natural way to define a completion. And so the point is, if you understand the complex algebra, you get, it could give you some handle on the C-star algebra. And the algebraic Nekrashevych algebra generalizes a family of algebras introduced by Bill Leavitt in the 60s called Leavitt algebras, which I will talk about. There's a whole, Leavitt path algebras are very popular now in ring theory. There's even a new subject classification in the 2021. I think semigroup still doesn't have a subject classification. Well, I guess we have some sub ones. People who study the algebraic versions besides Nekrashevych are Clark, Axel, Pardo, Sim, Starling, me and Nora, the authors, and there are other people too in ring theory. So let me first tell you what a Leavitt algebra is, because I need Leavitt algebras to tell you about, or to motivate these guys. So let me draw you a picture, if I can get my picture back on. So we're going to do computer science for a second. So I hope nobody objects to computer science. So I can think of an infinite word as a stack, an infinite stack, right? An infinite word is an infinite stack. Now, given any letter, there are two things you can do with a stack. You can push things and you can pop them. So let's say, so I have an operator, let's call it, which I write as x top. For each letter x, I get an operator which just pushes x to the top of the stack. So I just pushed x to the top of the stack. Okay, that was a bad idea. I guess I got to erase my stack. Sorry about that. I'm sure there's a more intelligent way than to use Zoom's annotate notations to do this, but we also have an adjoint operator, x star, which pops the letter x if there's an x to pop. And otherwise, it doesn't know what to do. It cries and it says garbage, and it gives 0. So imagine if my stack looks like this, and I try to do this x star guy, what I'm going to do is I'm simply going to, that's not my eraser. Okay, if I can, this effect would look better if I'm able to click on the eraser, but I'm going to pop the x. So I erase it. All right, that didn't work so well. All right, and I didn't want to redo that. That was a mistake too. But now, oops, all right, now I got carried away. Suppose instead that my stack began with a different letter, like y. And now I want to pop x. Well, I can't pop x because it begins with y, so there's no x to pop. So that's 0. Okay, so that's what that formula is saying. So if there's an x at the front, you pop it. If there's no x at the front, you say garbage, and garbage means 0. Oh, I don't want to put that stuff back.
Well, what happens to the stack?
So, well, I'm actually working in the vector space with basis x omega, so I'm telling you how elements act on the basis. So when I get 0, that just means I get the 0 vector in this vector space. So the stack disappeared. When we get a garbage answer, it means ignore that computation. A general element of this algebra will be a sum, which means you can sort of think of that as kind of an OR. So it's not a precise model, but computer scientists did actually use this algebra to model automata. I mean, push down automata. So here are some operations that relations that these operators satisfy. The first one says that y star x is delta xy. This is a Kronecker delta. What it says is if I try to put x at the beginning of the stack and then remove x, well, there was no point in putting that x at the front. I just get back what I started with, right? But if I put x at the beginning of the stack and then I try to remove a different letter, that's garbage. So that should be 0. So that's what that relation says. It says if I put a letter on and then pop it, that doesn't do anything. And if I try to put a letter on and pop a different letter, I always get garbage. I think I have one more undo to do. There's one other relation that's less obvious, which is called the Kuntz-Krieger relation, because Kuntz, in his Kuntz algebras, introduced it and was totally unaware of Leavitt. So this is called the Kuntz-Krieger relation. If you ever look at a C-star algebra paper, you'll almost certainly find this somewhere because it's one of the most popular C-star algebra. So what's this relation say? But it says, well, what this operator does is you pop the first letter on the stack and then you push it back on. So if I have my stack, blah, 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 with x on the front, this x will pop it and then I'll put it back on. But all the other terms will say garbage. So exactly one term will remove the x and put it back, and the other terms will say garbage. So the net effect is you're not going to do anything. So you have this other relation that's kind of a mystery relation at first, but you should think of that sum as an OR because these are actually orthogonal idempotents, if you're familiar with ring theory, and they add up to 1. And the algebra defined by these two relations, so generators x and x star guys, so little x's and little starred x's, and these relations is called the Leavitt algebra. And it's a finitely presented simple K algebra acting faithfully on Kx to the omega. So this algebra is finitely presented. You see only a finite list of relations, and it's simple. And Leavitt's interest in this is that it has the property that if you take the free module on one generator, it's isomorphic to the free module on the size of x generators. But no smaller positive value of x has that equality. So it's kind of a finitely presented example that fails the invariant basis number, which is something that, you know, and it has weird K theory. Well, depends what you mean by weird, but interesting K theory. Another interesting thing about this is that the group of units of this group contains Thompson's group Vx. So this is the version of V where you have an X, where you work with X-array trees. I've been drawing trees this whole time, so that should not surprise you if you're familiar with Thompson's group. Nekrashevych simultaneously to Berger made the observation that Thompson's group V embeds in the Kuntz algebra in the same way. And this is kind of, if you know how Thompson's group V acts on x to the omega, then the way it embeds in this group actually is the same action on infinite words. Thompson's group V, what you're allowed to do is pop a prefix and replace it with a new prefix. So you can write guys in Thompson's group V as certain sums of this form. So it embeds in the group of units. And this Leavitt relation, the Kuntz-Krieger relation, this is exactly the caret replacement rule. Putting these XX stars is putting a caret at the end of everything. And saying it's equal to 1 says you can remove the caret. So if you look at the embedding, you'll see that this relation is the caret thing. So I don't have time to define Thompson's group V, but at least I know some people here are familiar with it. Okay, now to get to Nekrashevych algebras, well, we have a group of automorphisms of the tree, whether it's self-similar or not. Since x to the omega is the boundary, it acts on x to the omega by permutations. So we get a permutation representation or a permutation module acting on x to the omega. So a natural thing to do is to look at the algebra generated by G and the Leavitt path algebra. So the group acts on this vector space, the Leavitt algebra. There's no path in this case. There's something more general where you allow words over infinite words over a graph instead of a set. So sorry, if I say path, that's what I'm talking about, but I don't mean to talk about it here. So I claim it's natural to look at the algebra generated by G and LK of X. And this idea has been used before if you're familiar with Klaus Rover's work. He starts off with Grigorchuk's group, which acts on the 2-letter alphabet, and therefore acts on 0, 1 to the omega, and so does V. And he looks at the group generated by these and gets it that it's like essentially a simple group. And since Grigorchuk's group acts on 0, 1 to the omega, and V lives inside the Leavitt algebra, what I'm doing here is a generalization of that. Now, if you, in addition to the Leavitt relations and the group multiplication, there are some additional relations that come from the self-similarity of the action. So here's one relation. If I have an infinite word W, so this is my stack, and then I act by X, and then I act by a group element, well, we know how this is going to act. This is going to be, you're going to have G act on X, and then its section acts on what's left. So that's what this relation says. The action of G times X is the same as the action of GX times G restricted to X, okay? Because remember, W is the guy it's acting on. So that's that relation, and this actually tells you the whole self-similarity structure. So it's encoded in this relation. There's a dual relation for erasing, which is a little bit harder to draw, but you can think it out. It says that if I try to erase an X and then do G, that's the same thing as doing G inverse of X star and then doing a certain section. It's the dual relation to one, but it's not as obvious, so you have to think about it. I mean, it's easy to do, but not maybe on a slide. So the Nekrashevych algebra, which I'm calling N for Nekrashevych, N sub K of GX is the K algebra generated by my group G. These funny letters corresponding to these X's and X stars corresponding to X. And then I do the Leavitt algebra relations and the group multiplication table. That's what I mean by generated by G. And these two relations, the self-similarity relations. Okay, so it's given by a presentation. The good thing about giving an algebra by presentation is you can write down lots of representations. All I need is a representation of the Leavitt algebra, and these are well understood, and a simultaneous representation of the group so that this extra self-similarity relations are satisfied. Now, it turns out that the algebra generated by the Leavitt algebra in G is not always the same as the Nekrashevych algebra. In fact, me and Nora, we showed that the algebra generated by LK of X and G is simple, and it's the unique simple quotient of the Nekrashevych algebra. So the Nekrashevych algebra has a unique maximal ideal, and its quotient is the kernel of this action. In the C-star setting, there's sort of an analogous result in Nekrashevich's paper, but because X to the omega is uncountable, C-star algebraists don't like to act on non-separable Hilbert spaces, so he kind of works with a certain subspace of X to the omega. But somehow the spirit is similar, but the technical details are different. Okay, so simplicity of the Nekrashevych algebra, which is the question I'm interested in this talk, is equivalent to the faithfulness of this representation on infinite words. And let me also mention that simplicity of the complex Nekrashevych algebra is known to be necessary for simplicity of the C-star algebra. So that's another reason to study simplicity, is because C-star algebra people care about these things. And actually there are people in C-star algebras who are not equal to Nekrashevych who study these C-star algebras. So it's not like he introduced them and nobody else looked at them. All right, these are some words that I'm just going to say, but I'm not going to talk about. So étale groupoids, these are certain sorts of topological groupoids. A groupoid in the sense of category theory. So it's a small category where all the objects are invertible. People in C-star algebra theory, they know how to assign C-star algebras to étale groupoids, and Nekrashevych showed in his original paper that his algebra is the algebra of a certain étale groupoid. It's a groupoid of germs, for those who know these kinds of things. And Nekrashevych, you can also define groupoid algebras over rings. For some reason, I was the first person to bother doing this, and so now lots of people are calling these Steinberg algebras. I don't think that's an accurate name, but that's what you can find in the literature, so just be on the lookout. But anyway, étale groupoid algebras, if you take the same étale groupoid as what Volodya used for the C-star algebra, you get the ring. And it's already kind of been observed that there's a lot of connections between the ring and the C-star algebra. In particular, unfortunately, the topology on these groupoids can be weird. They're not always Hausdorff. The groupoid for a self-similar group satisfies the conditions that are known to be equivalent to simplicity of rings and C-star algebras and for étale groupoids when they're Hausdorff. But these groupoids that you get from self-similar groups are not normally Hausdorff. So another motivation for studying their simplicity is their good test case to try to understand what happens when things are not Hausdorff. So that's kind of the motivation. But again, if you don't know about C-star algebras, you can forget about the motivation for the rest of the talk. So what I wanted to say something about now are previous results. So in 2015, Volodya Nekrashevych proved that the Nekrashevych algebra of the Grigor-Chuk group is not simple and characteristic 2. This was actually kind of interesting because nobody knew of examples of non-Hausdorff groupoids which satisfied the known conditions, but which were not simple. So I'm going to explain to you in terms of this representation why this is the case, assuming you know a tiny bit about the Grigor-Chuk group. So the Grigor-Chuk group acts on the alphabet 0, 1, and it's generated by a Klein 4 group B, C, D, and E, where E is the identity, which has the property that it fixes the infinite word 1, 1, 1, 1, 1, 1, 1, 1, 1, and on any other infinite word, exactly 2 of them agree. So 2 of them fix the word. So 2 fix any infinite word W, not equal to 1, 1, 1, 1, 1, and 2 flip the first symbol after a 0. Now, which 2 do what depends on what is the remainder, what is the value mod 3 of where the first 0 occurs. But it's always the case that 2 of them fix it and 2 of them flip the first symbol after a 0. So let's see how these, so then I'm going to use this to basically construct an element of the Nekrashevych algebra which acts as 0 on infinite words under the representation we saw before. So take the element B plus C plus D plus E. Then it actually annihilates all infinite words in characteristic 2. If you act on 1, 1, 1, 1, 1 by this element, let's call this, no, A is a bad letter. Let's call this thing, I don't know. Let's call this thing Z. If you act on 1, 1, 1, 1, 1, since they all fix it, you're going to get 4 times 1, 1, 1, 1, 1. But in characteristic 2, that's 0. If you act on any other word, let's say there's some, and there's a 0 and blah, 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 you're going to get 2 times your original word plus 2 times flip after 0. After first 0. But again, that's 0 mod 2. So this element annihilates all infinite words. Now you have to do something to prove that this element is not 0 as a consequence of the defining relations. But you can do that. So I'm leaving under the rug. There's a characterization of which elements satisfy the defining relations, and you can check that this guy does not. But that I'm not going to prove to you. I'm just proving to you that this thing annihilates all infinite words. Okay. Clark, Exel, Pardo, Sims, and Starling in 2018 proved the Nekrashevych algebra of the Grigor-Chuk group is simple over fields of characteristic different than 2. So 2 is the only bad characteristic for this group. And then Nekrashevych, they also showed the Nekrashevych C-star algebra of the Grigor-Chuk group is simple. Then I guess Nekrashevych, who probably was the referee of their paper, sent them an email showing that the Nekrashevych algebra of the Grigor-Chuk-Ursuler group is not simple over any field. So the Grigor-Chuk-Ursuler group was defined by Grigor-Chuk, but its exact degree of growth, if I understand this correctly, was computed by Ursuler. So people tend to call it the Grigor-Chuk-Ursuler group. And it's kind of a cousin of the Grigor-Chuk group in the sense of you look at the automaton, it looks pretty similar, but it behaves somewhat differently. And this was the first example I know of that kind of was not simple over any field. And yet its groupoid satisfied all the conditions that were known to give simplicity for Hausdorff guys. So this kind of begs an explanation. What exactly does happen for self-similar groups, especially contracting ones, because those examples are all contracting. So let me point out that Nekrashevych showed in his original paper that the C-star algebra of a contracting group is finitely presented. And his same thing works for algebras over a field. The same proof works because it just plays with the defining relations. The algebra is generated just by the letters and their stars plus the nucleus. And the relations are you take all the relations I had before, so the Leavitt algebra relations, but you only involve group relations and self-similarity relations with nucleus elements. Oops. So for instance, if I have n prime and n double prime, n times n prime in the nucleus, then I throw this relation in. But the nucleus is not close under product. So I don't put in a relation. If this is not in the nucleus, which often happens, I don't put a relation in. I also have the self-similarity relations restricted to the nucleus. Since the nucleus is close under sections, those relations make sense. And so this gives a finite presentation because the nucleus is finite, and you can show it presents the same algebra. Requires a little bit of work, but not a lot of work. And so since the nucleus is finite, you get a finite presentation. I left out the self-similarity ones, but you can also you have to put those in as well, but just the nucleus ones. And the algebra depends only on the nucleus, not the group. It's not in general true that a contracting group is generated by the nucleus. If it has an extra property called self-replicating, then it is. But in general, it doesn't have to be. You can kind of have some extraneous elements that don't survive into the nucleus or aren't generated by the nucleus. So here's a first theorem. We have better theorems than this, but this is a theorem I can state at this point. So here's our first theorem. Let G be a contracting group over the alphabet X. Then either the Nekrashevych algebra is not simple for any field, like this was the case of the Grigorchuk-Oechsler group, or it's simple for all fields except for finitely many positive characteristics, like what happened for the original Grigorchuk group. Okay, so it's not possible for it to be simple, for it to be non-simple in characteristic 0, but be simple in characteristic 2. As soon as it's simple in characteristic 0, it's simple in all characteristics. And if it's not simple and if it is simple over characteristic 0, then there are only finitely many bad primes. That's what this is basically saying. This, I guess, maybe is not that surprising because the algebra is finitely presented, but I don't know a general proof just from finite presentability. I'm finitely presented with the relations all over Z, but I don't think that implies that. The second theorem is that there's an algorithm which on input the nucleus of G outputs the set of characteristics for which the algebra is not simple. So it will either tell you it's never simple, or it will give you that finite list of primes for which the algebra is not simple. So in geometric group theory or combinatorial group theory, we like algorithms, right? So we want to know things like, you know, is it simple? And the answer is, well, if you input the nucleus, then you can decide. And remember, if you have a contracting group given by any automaton, you can build the nucleus, assuming that you're promised that it's a contracting group. So this algorithm, you know, you could allow the automaton as input as long as you have an oracle to knowing it's contractible. And there's also a theoretical description of simplicity that's more complicated to state that I may or may not get up to, and that underlies the algorithmic result. And you can apply this to infinite families of contracting groups. An algorithm will tell you any specific group is whether it's simple or not, but it won't tell you what happens for an infinite collection. But we can basically figure out what the algorithm would tell you for many infinite families. So in that sense, you know, we're okay. And also for any finite set of primes P, we construct an example of a group which is, of a contracting group which is simple precisely over those fields whose characteristics are not in P. So probably I won't get up to the technical stuff, so you guys are gonna be lucky, I think. What time do I stop, Ilya?
At 5 o'clock. So
oh, it's at 5. Yeah. Oh, I thought I stopped at 4:50.
No, you have 60 minutes.
Oh, okay. Then I will get to the end. So let P be a prime. So I'm going to tell you about Sunic groups because these are very interesting groups. In particular, since I saw Zoran here, or I thought I saw him there, so that makes them even more interesting. But also because they're nice examples that generalize both the Grigorchuk group and the Grigorchuk-Oechsler group, and where we can say exactly what happens. So P is going to be a prime. And I'm going to take a polynomial over Z mod P. That is not the p-adic numbers. So if you're a number theorist, I apologize. That's Z mod P of degree greater than 0. And it should have a non-zero constant term. That's important. And I'm going to use MF to be the companion matrix of F. So that matrix we all learn about in linear algebra class. And then I'm going to build a self-similar group with alphabet ZP, which is generated by a cyclic permutation of the trees. So the guy sigma, he's going to just move this guy, each guy over 1, and the last guy back to the beginning in a completely rigid way. So it's going to, if I act on a word, let's say this way, it'll just be x plus 1 times w. So it acts completely rigidly. It just adds 1 mod p to the first letter, and then it does nothing else. That's how sigma acts. So if you're familiar with the Grigorchuk group, you know that he has a guy like that in his group. Okay, this undo thing's a little bit slow. I guess I shouldn't do too much drawing. And you also have a copy of ZP to the n. This is like that Klein-4 group and the Grigor-Chuk group. And the way it works is that, so I take a vector V in ZPN, and the section of V, and it's going to fix the first letter of each word, so it stabilizes the first level of the tree. Its section at 0 is you multiply V by the companion matrix. So here you're going to get, this is a picture of what V looks like. So here you're going to do MF of V. Here at the very end, you're going to do sigma raised to the power of the last component. And every place else, you're going to do identity. So it's a similar picture to the Grigor-Chuk group, except that Grigor-Chuk likes to put the interesting stuff at the last thing and the uninteresting stuff at the first thing, and Zoran does it the other way. Probably makes it easier to write the paper to make the interesting stuff happen at the beginning, if you have more than a binary alphabet. So this gives you a contracting group with nucleus ZP to the n, Z mod P to the n, and sigma, the group generated by sigma. You need the whole group generated by sigma. The Grigor-Chuk group is the group you get by making your prime 2 and your matrix 1 plus x squared. This is the minimal polynomial of the unique, or of one of the primitive elements of the 4-element field. And the Grigor-Chuk-Oechsler group is the one corresponding to x squared plus 1. Another famous group, the Fabrikowski-Gupta group, is G3x minus 1. There are probably other famous groups in this series, but here are some of them. And Zoran gave necessary and sufficient conditions for GPF to be a P group of intermediate growth. Actually, he gave separate conditions for P group and for intermediate growth, but I put it all together to save time. Okay, so here's a theorem that tells you what happens for these guys. So let's take the Sunic group GPF, where the degree of f is n. If the degree of the polynomial is 1, like the Fabrikowski-Gupta group, then this Nekrashevych algebra will be simple for every single field. In the case that n is greater than 1, if the companion matrix acts transitively on the lines through the origin in ZPN, so on the projective space for ZPN, then this Nekrashevych algebra will be simple for all fields except those of characteristic P. So this is what happens for the Grigor-Chuk group. For the Grigor-Chuk group, the companion matrix looks like this. And this guy acts transitively on the 3 vectors, the 3 non-zero vectors in the Klein-4 group. And so that's why it's simple in all fields except those of characteristic 2. And for any prime P, you can find a similar matrix called, or similar polynomial, which will act transitively on all the non-zero vectors, called either a Singer cycle or a primitive polynomial. Now, in the case that MF does not act transitively on projective space, then the Nekrashevych algebra is never simple. This is what happens for the Grigor-Chuk-Oechsler group. In this case, the companion matrix for x squared plus 1 is this permutation matrix, and it fixes the vector 1, 1, so it does not act transitively, and that's why Nekrashevych found that the algebra was never simple. So it's a very simple criterion in terms of the companion matrix. And it turns out from Zoran's result that if n is greater than 1 and MF acts transitively on this, then GPF will be a P group of intermediate growth. This is stronger than Zoran's condition, although I think it's equivalent when the n is equal to exactly 2. The Grigor-Chuk-Oechsler group, as I said a second ago, is not simple because it fixes something as companion matrix. So there are other families of famous groups we studied. We showed that group the Sikhi P groups, if you're familiar with them, and more general GGS groups over prime size alphabets have simple Nekrashevych algebras over every field. But if you allow GGS groups over alphabets which are not prime powers, then either the algebra will be simple over all fields or none. And I can tell you based on the defining data, for those who know what GGS groups are. If you don't know, don't worry about it. We also characterize simplicity for self-replicating spinal automaton groups. You don't have to know what that is. And something called multi-ed spinal groups, which generalize GGS groups. Anyway, these are just names. This is just to say that, you know, there's a non-empty set of classes for which we know the answer. Okay, so this is the part nobody really wanted me to get to, but since you're giving me till 5, blame it on Ilya, which is the semi-group part. So of course, we solve all the problems using semi-group theory. That's the moral of the story. So if I have a self-similar group inside of OTX, the Nekrashevych algebra, I remind you, is generated by the group and these letters and their stars subject to some relations. Just for convenience, I'm going to define the star of a word to be the reversal with stars, okay? So the usual thing you would do with an involution. Then the defining relations for the Nekrashevych algebra are the multiplication table of G, this self-similarity relation, the dual one, and then these two relations from the Leavitt algebra. All of these relations, except for the last one, the Kunz-Krieger one, except for number 5, they only involve multiplication. There's no addition except for in the last one. So if you just take the relations 1 to 4, you're defining a monoid algebra. Or technically, it's a contracted monoid algebra because the 0 of the monoid and the ring are the same. So there's a name for when you make the 0 of the monoid the same as the ring. And then the Nekrashevych algebra is just the monoid algebra mod this extra relation. So mod the ideal generated by that relation. And the monoid's easy to understand. It consists of 0 and all elements of the form UG V star, where G is a group element and U and V are words. It's a shame that X star is used for the free monoid, and they also, the C star algebra people use star here. So there's no relationship between the two uses of star. Okay, and it's easy to see why all monoid elements are of this form, because relation 2 says that I can move a group element to the right of a letter, and rule 3 says that I can move the group elements to the left of the star letters. And that means I can always put group elements in the middle. And relation 4 says that a star letter times a positive letter is either 0 or 1. So I never need to have star times positive. So you can, this presentation is essentially Knuth-Bendix, and those are the normal forms. You know, modulo, since I put the whole group multiplication table in. Okay, now I need another definition, which probably is not familiar to people here, but maybe some people know. A monoid is called an inverse monoid if for every m, there's a unique element m prime, so that m prime m is m, and m prize m prime equals m prime. So this is kind of relations often associated with Penrose inverses, who just won a Nobel Prize. And actually, Penrose wrote an important paper on inverse semigroups with Douglas Munn in the 1950s. So he proved something important about inverse semigroups, so I got to fit him in. Ha. Groups are inverse monoids, where the m prime is just the usual group inverse, but they're more general. Inverse monoids are to partial symmetry as groups are to symmetry. So the partial automorphisms of some space or structure form an inverse semigroup, while the automorphisms form a group. This funny MGX guy is an inverse monoid. It acts on the Cantor space by partial automorphisms. If you take this guy here, this is really defined on infinite words that start with V, and it will produce an infinite word that starts with W by just erasing the V, applying G, and putting, sorry, that should be a U. And put, well, that was supposed to be a U. And put the U back. Okay, sorry, that was supposed to be a U. I erased my eraser. Okay, anyway, I said it, it's not worth trying to get it correct. It takes up too much time. I guess I shouldn't use the annotation anymore. It takes up too much time to annotate. Okay, now this inverse semigroup is not any old inverse semigroup. It has the property that it has no proper quotients. So an inverse semigroup, we call it congruence free. In group theory, you'd call it simple. In ring theory, you'd call it simple, but simple means something else in semigroup theory. Now, this funny ideal with the Kunz-Krieger relation is also special. It's an example of what's called Exel's tight ideal. So this is an ideal that Exel associated to any inverse semigroup algebra. He actually did this for C-star algebras, but then you can do it for rings. And I proved with Nora that if you have a congruence-free inverse monoid, so an inverse monoid with no proper quotients, then there's a unique maximal ideal which contains this Exel ideal, which we call the singular ideal. So in particular, this tells you that there's a unique maximal ideal in the Nekrashevych algebra. And for the case of Nekrashevych algebra, or in this monoid algebra, the singular ideal is the kernel of this action on infinite words. And we have an explicit characterization of these two ideals as follows. So an element of the inverse monoid algebra belongs to the Kunz-Krieger ideal, satisfies this relation, if and only if all sufficiently large words annihilate A on the right. And it's singular if given any finite word U, you can make it longer so that you are killed by A. So the first condition says all sufficiently large words kill A. And the second one says any word can be continued to a word that kills A. And our key reduction is that if this algebra is not simple, there's an element of the group algebra which witnesses this. That means there's a group algebra element which is singular, it belongs to this maximal ideal, but it's not 0 in the Nekrashevych algebra. And for contracting algebras, we're able to show that if there's a bad element, if there's an element in this maximal ideal, then it's supported on the nucleus, which is a finite set. So we reduce everything to a finite problem. So probably I'll stop on the next slide because I don't know, we'll see. So just to give you the idea of the algorithm and not the details, if n is the nucleus, it's a finite automaton. This condition to be singular, meaning that any word can be extended into a word that kills you, is given by turns out to be given by a finite system of equations, of linear homogeneous equations over Z. In fact, the coefficients are all zeros and ones. And this condition to be in the ideal generated by the Kuhn-Krieger relations given by a larger Z linear system, E prime, which encodes that all sufficiently large words kill your element. And since then it's easy to check whether there's an element which is singular, so it solves it's a solution to E, but it's not a solution to E prime, meaning it's non-trivial. All you have to do is check that the ranks of the coefficient matrices are different. And since these are 0, 1 matrices, their ranks are the same as over Q for all but finitely many primes. So that's why there's only finitely many primes where things are different. Now I was going to see how you get the system of equations, but I don't know if it's worth going into it. Well, I guess I'll put up the slide, but don't try to read it. The idea is we construct a finite automaton in the sense of language theory that recognizes those words which kill the element A. So if you're given an element A supported on the nucleus, we build a finite automaton which recognizes those words that kill A by right multiplication. And then we're able to determine whether your element was in the Kuhn-Krieger ideal or singular by examining the nature of this automaton. The formal way we do this is we let the free monoid act on equivalence relations on the nucleus by saying that the action of X on an equivalence relation X is if you take two nucleus elements, we say they're equivalent if the two elements agree on X, and when you restrict, and their sections are equivalent. And okay, it's a little bit technical. Then we define the equivalence relation associated to W to be the image of W under the equality relation. And the key point is G is W equivalent to H means that G restricted to words beginning with W is the same as H restricted to words beginning with W. So they have the same germ on neighborhoods of W. That's roughly what it means. And anyway, since n is finite, there are only finitely many equivalence relations. And the orbit of X, I think I'm running out of time. So maybe it's not worth going into how we build the automaton, but roughly speaking, we draw a Schreier graph of this action. And then certain vertices, the ones which you can reach from cycles, we have to make them accepting if we want our element to give us something which is in the Kuhn-Krieger ideal. And we have to make all the elements in minimal components, strongly connected components you can't leave. We have to make those accepting to be singular, and that's how we tell. But anyway, there's no time, so we'll skip that. I'm only 2 slides from the end, so I'll stop.
All right, thank you very much. Things done for the talk. Okay, now if there are any questions, you're welcome to ask them.
Can I ask something?
Sure.
Hi, Ben. Thanks for the talk.
Hi, Zoran.
I have a simple question. Those groups that come from polynomials, you said when the degree of the polynomial is 1, you always have simple algebras.
The algebra associated is always simple. That's right.
Is it even true when P is 2?
Even when P is 2, if the degree of the polynomial is 1, not the group algebra is simple, it's the Nekrashevych algebra, which is simple.
Ah, okay. Because
the group algebra is never simple, of course.
No, of course. But
no, yeah, even in the characteristic that you think should be bad, it's still good. In fact, those ones are probably even Hausdorff, I believe, when it's degree 1, which would make it fall under the old results. Yeah, I mean, the key point is that the homomorphism you use is essentially injective. The non-trivial section is injective, and that makes everything simple. Okay. The projection to the last coordinate is actually injective when n is equal to 1.
My point was P equal 2 and n equal 1 is a weirdo because it's just the hedral group. It's not.
Yes, but the algebra is. But remember, if the group is trivial, then you get the Leavitt algebra, which is simple.
Okay.
It's not, the group doesn't have to be strange. It's the action that has to be strange to make it not simple.
Okay.
So yeah, it's the connection between the group algebra and the situation with this Leavitt algebra are a bit strange. And the group algebra actually embeds in that particular case. Sometimes the group algebra does not embed in the Nekrashevych algebra. Sometimes there are group elements which satisfy the Kunz-Krieger relation. But in that case, it doesn't. But yeah, the simplicity is coming because of the Leavitt part, not because of the group doesn't foul it up. Yeah, if your group theorist is counterintuitive, you should think that, you know, anything that's too simple shouldn't have a simple algebra. But it's the Leavitt part that's making it simple. Somehow it's when the action on the group is bad. It has something to do with the nature of the germs at infinite words and how they interact.
All right. Are there any other questions?
May I ask a question?
Sure.
Yeah, so you mentioned that, hello, thanks for the talk. This is Chen Chao Wu. You mentioned the hope that that this will give us some insight into how into the simplicity problem for non-Hausdorff groupoids. So I just wonder if we can actually read off some insights, say, from the point of view of the dynamics of the groupoid.
So the simplicity condition can be phrased in groupoid language. So in this paper, both Nekrashevych and also Axel, Pardo, Clark, Starling, Sims, and maybe I'm missing, I don't think I'm missing any names. For non-Hausdorff groupoids, they came up with an ideal, which they're calling the singular ideal, which corresponds topologically to my algebraic ideal, which consists of those functions whose support on the groupoid, which belong to the algebra, but whose support have empty interior. And these guys are what cause the non-simplicity. And it seems to be, but we don't have a concrete exact explanation. Valeria also asked me about this, as to how that is reflected in the dynamics of the action. And it seems to be something about, so it's related to the existence of the isotropy groups. So somehow you have to have elements in the algebra which have in their support non-trivial isotropy elements. And that's kind of a weird thing, because for these groupoids, in the second countable case, the points with trivial isotropy are dense. So it's kind of counterintuitive. So you need some weird isotropy, which is weird enough and happens in enough areas that it pops up in the groupoid algebra. And our condition in the contracting case, there's enough kind of because of the finite stateness of the automaton, the bad behavior crops up enough that you can construct elements of the algebra which witness this non-trivial isotropy and still belong to the algebra. I don't know if that makes any sense. I think it's still not super well understood, but at least we now have infinitely many examples of groupoids that are non-Hausdorff, minimal and effective, essentially principal, but still not simple algebras. Even their C-star algebras are not simple.
I see.
As soon as the complex algebra is not simple, the C-star algebra is not simple.
Right.
And then we had lots of examples like that now, tons of examples. So at least we have a lot more examples, but somehow in order to get a very nice characterization, we dropped the groupoids and went to the inverse semigroup theory. Mm-hmm. And probably you could do that with groupoid algebras as well, if your groupoid's ample. I think you can also go to the inverse semigroup algebra and see it living in there. Although once you complete the inverse semigroup algebra, I don't know if that's as helpful.
So you said in the non-Hausdorff case, there's this kind of bad actor that comes from this ideal. What do you call it? I forgot. But,
so Axel calls it the gray ideal. In the original paper, they called it the ideal of singular functions.
Is this the only bad actor in that? Yeah,
it's the unique maximal ideal. It's the unique maximal ideal. They essentially prove it. They don't say it, but it's essentially, you can easily modify their proof to see that it's a unique bad actor.
So when it's not simple, is the ideal lattice kind of small, or in general?
Well, I don't know how much is between that. So Axel has proposed that you just factor out that bad ideal. And he has a name for that C-star algebra. Him and David Pitt, I forget what they're calling it. But I think it's not known exactly how big the lattice in between can be.
Okay, thank you very much.
All right. Okay, let us thank Ben again.
Thank you.
All right, thank you, Ben. So now I'll stop the recording. 1 moment.
I guess I should stop sharing my screen, right?
Yes.